Ampere's circular law. Now, Ampere's circular law is used to find the magnetic field. Earlier, we have studied Bio and Sarot law to find the magnetic field. So, now we will study the Ampere's circular law or Ampere's circulation law. Now, according to Ampere's circulation law, the line integral of magnetic field in a closed path is equal to mu 0 times the sum of the current in the closed loop. Suppose this is a closed loop. Here current I1, I2, I3, I4 they are passing. Now the direction of I1 is positive, they can take negative, this is negative, this is positive. So total current will be equal to I1 minus I2 minus I3 plus I4. So the outgoing which we have taken positive and downward we have taken negative. So the line integral is written as integral and there is circle. It is made for the closed path B dot dl. B is the magnetic field and this is a dot product. B vector dot dl. This is equal to mu 0 multiplied by the summation of I. Or we can, for this purpose, this is the closed path. This is the closed path, and for this closed path, we can write the line integral for the closed path B dot dl is equal to mu 0 times I1 minus I2 minus I3 plus I4. So here it is the arithmetic sum of the current in the closed path. If the current is outside, then that current is not to be taken. We have to take only the current which are included or which are inside the closed path, and this is your closed path. Now we define what is the line integral. So in mechanics, suppose this is the field and force is changing and we are moving from A to B. At this point we take a small distance dl, F is the direction of force, then the line integral will be, the work done will be equal to F dot dl integral from A to B. From A to B, this will be equal to work done for A to B. Now here it is not a closed path, it is open path. It is a on path from A to B. It is not closed. Closed path will be then when we come back B to A. And here if we go from A to B here and B to A here, then it will be closed path. So for the closed path, the work done, then we will write the integral and circle here, the F dot dl, this will be equal to 0. Because in mechanics, we are starting from this point and end at this point. So the net displacement is 0. So work done is equal to 0 in the case of the force in the mechanics. Because the force is a conservative force. Here we will take the line integral of B dl, and here B is not conservative. So the line integral of the closed path B dl will not be equal to 0. It can be equal to 0 if B and dl are perpendicular to each other, because B dot dl is B dl cos theta, and when theta is equal to 90, it will be equal to 0. So otherwise, if the theta is not equal to 90, B dl for the closed path will not be equal to 0 in the case of magnetic field. Now we have earlier studied the magnetic field, and earlier we have studied the electric field, and now we are studying the magnetic field. Electrical field was due to the charges, and we find the electrical field using the Coulomb's law. Now here we find the magnetic field, and magnetic field is find by the Bio and Savart law, which we have studied earlier. Now we can also find the electrical field by Gauss law. Here we can find the magnetic field by using Ampere's circulatory law. So the line integral of this is surface integral, not line integral. Surface integral of, you can write here S. That will be more proper. So the surface integral E dot ds, here ds is area vector, is equal to summation of q bata epsilon 0. And in the Ampere's law, circular law, the line integral of V dl, we can also write here an L. L represent the line integral, S represent the surface integral. So this is line integral, and this will be equal to mu 0 times summation of I. Here this is summation of current, here this is summation of charges. Electrical field is inversely proportional to epsilon 0, whereas magnetic field is proportional to mu 0. So here it is mu 0 times summation of I. Here it is summation of mu 0 divided by epsilon 0. Epsilon 0, it is for the free surface, and here also we have taken the, if the surface is not free surface, then what will be the result? We will write this will be equal to mu into 0. Mu 0 will be the permeability of the medium, and mu 0 is the permeability of vacuum or free space. Now we can find the Ampere's law by Bio and Savart law. We can deduce the Ampere's law from Bio and Savart law. In Bio and Savart law, we have considered, suppose this is a long conductor whose length is infinite and it is very thin. This long infinite current, I current is passing through, then the magnetic field at a distance B, at a distance capital R, for this we take is path, circular path, and V will be same for each point on this path. So the line integral of B dot dl will be equal to the magnetic field B, we have found it, and P is equal to mu 0 bata 4 pi 2 I bata R, which we have found earlier. Dot. So we will, instead of dot, we will write B dl cos theta, and here the direction of B will be always tangential to the path. So B and dl will be parallel, so angle theta will be equal to 0. So it will be equal to mu 0 bata 4 pi 2 I R dl cos 0, and cos 0 is equal to 1. So here the angle is equal to 0. Now what will be the value of dl? Mu 0 is constant, 4 pi is constant, 2 I is constant, R is constant. dl will be equal to 2 pi R, and if we substitute 2 pi R, then this will cancel. 2 pi cancel, R will cancel, mu 0 cancel, this 2 will cancel, and I will be there, so it will be equal to mu 0 into I, which will show line integral of V dot dl will be equal to line integral of V dl, because in scalar product V dl cos theta, and as I have discussed earlier, then theta is equal to 0, cos 0 is equal to 1, so it will equal to P dl. Now P is constant for the entire circular closed path. So we have taken B outside and dl. The value of B will be equal to mu0 bata 4 pi 2I bata r, where r is the radius of the circle. Then integral will be equal to dl, because all these quantities are constant. So dl will be the total length of the circle, and that will be equal to the circumference. So it will be equal to mu0 bata 4 pi 2I bata r into 2 pi into capital R. R cancel, 4 pi cancels. So it will be equal to mu into I. So the line integral of V dot dl is equal to mu0 into I. Here only there was one current, so it is I. If it is more current which are passing through this circular path, then that will be equal to summation of I. So we can derive the Ampere's circular law with the help of Bio's law. And this thing is not covered in your book, but I am giving you this derivation. Now we have to find the magnetic field of an infinitely thin conductor. And suppose this is the thin conductor, means whose area of cross section is negligible, and we have to find the magnetic field at this point. So first of all, what will take it? If this distance is suppose capital R, then we will have a closed circular path, and closed circular path will be a circle of radius R, and this path is known as the Ampere loop. Similar in the Gauss, we have find the electrical field using the closed loop. Here the closed loop is your Ampere's loop, and that will be the closed surface for this, because the integral was with the surface. Here integral is with the length. So we will take, this is an Ampere loop, and it is a circle whose radius is capital R. Now according to the right hand thumb rule, if we take, then the direction of magnetic field will be, the current is upward, so it will be in the counterclockwise direction. So magnetic direction of magnetic field is counterclockwise. The magnetic value will be same at this point, or any point on the Ampere loop. Now if we take a small element dl, then we can find the magnetic field using the Ampere's circular magnetic field at a point which is at a distance r from this conductor, which is carrying current I, can be found with the help of Ampere's circulatory law. Now according to Ampere's circulatory law, the line integral of V dot dl is equal to mu0 into I, because only one current is there, so we will take I. Now here the directions of dl and V, they are in the same direction, or they are parallel. So angle between the magnetic field and small element dl is equal to 0. So it will be equal to B into dl cos 0, which is equal to 1, is equal to mu0 into I. So now since B is the same for all the points on this Ampere loop, this is the Ampere loop, similar to Gauss surface in the case of Gauss law. So we will take B outside, and line integral of dl is equal to mu 0 into I. Now, what would be the line integral? If we take the small different elements, then the total dl will be equal to the circumference of this circle or circumference of the imperial loop, and that will be equal to 2 pi into r. So this will be equal to p into 2 pi r, and which will equal to mu 0 into I. So p will be equal to mu 0 but 2 pi into I into r. So this will be the what would be direction? Direction of magnetic field will be from right hand thumb rule, and it will be inside the board. So we will give it across here. So this is the same magnetic field we have found earlier with the help of Bio and Sahart law. Now, if we draw the curve between B and R is the distance and B is the magnetic field, and B is proportional to I, and B is proportional to 1 by R. So, if we plot a graph between B and R, it will be like this. And if we plot the current graph between B and I, it will be a straight line because it is proportional. It is inversely proportional to R. So, it will be a hyperbola. This is proportional to 1 by R. So, it will be a hyperbola. And B will be equal to 0 as R becomes 0, means at this point it will be 0, and at infinity it will be equal to 0. So B will be 0 when R is equal to 0, means at the point of the conductor, and B will be 0 when R is equal to infinity. So in this way we have found the magnetic field of a infinitely long conductor carrying current I at a distance R, and that magnetic field is B is equal to mu 0 bata 2 pi R into I. And if the medium is not, this is for the free surface, free area, free medium or vacuum. If the medium is there, then B will be equal to mu divided by 2 pi R into I. So instead of permeability of the free space, here we will put the permeability of the that medium, or we can also write it B is equal to, B vector is equal to mu 0 into mu R into I divided by 2 pi R, where mu R is the relative permeability, mu 0 is the permeability of the free space or vacuum. So we can write the magnetic field for the other than free or vacuum, it will be equal to mu 0 into mu R into I divided by 2 pi R. So in this way, we can find the magnetic field of a conductor which is infinitely long, carrying the current I. So the magnetic field will depend upon two factors. One is the current, which is proportional to it, and another is inversely proportional to R. Means as R increases, as the distance increases from the conductor, the magnetic field decreases. We will find the magnetic field due to a cylindrical long current carrying conductor. Earlier we have found that when we have taken the conductor was very thin. Now here the conductor is not thin, its radius is R, capital R, and it is of the infinite, and I current is passing through this conductor. So I current will be same for the all part of the conductor. Now we have to find the magnetic field. Suppose at a point P, which is outside this slender. And suppose this distance we have taken smaller. This is the center of the cylinder, and distance of 3 point from the center of the cylinder is smaller. Then first of all we will construct a imperial loop. Imperial loop will be of the radius smaller, so it will be a circular of or circular in shape, and its radius is smaller. Now we will apply to find the magnetic field at point P. We will apply the Ampere's circulatory law. Now, according to Ampere's circulatory law, the line integral of B dl, B dot dl is equal to mu 0 to summation of I. Now here summation of I is same, current is same, total current which is passing through this cylinder will be same for entire this imperial loop, and that is equal to I. Now the direction of magnetic field will be given by the right hand thumb loop. So it will be like this. So it will be towards the inside the board. It will be inside the board, and it will be same inside the board at every point on the ambient circuit. The direction of B is tangential to DL. So the angle between B and DL is equal to 0. So the line integral will be equal to B DL cos 0, because angle is 0. We have this is the dot product, so it will be DL cos 0. This will be equal to mu 0 into I. And now cos 0 is equal to 1. So this is also equal to B. Now B is constant for each point on the imperial loop. So we take B outside. So B then line integral of dl. So this will be B outside, then line integral of dl is equal to B. Now to find the total line integral. Total line integral, as we have done earlier in the case of the thin conductor, it will be the circumference of the circle or imperial loop, that is equal to 2 pi into r. So the line integral for the closed path dl will be equal to 2 pi r, will be equal to mu 0 into I. So B will be equal to mu 0 I by 2 pi r, and its direction is perpendicular to the board inside. So this result is same as we have find if the conductor is a thin conductor whose radius is negligible, or it is a cylindrical whose radius is capital R, and the point where we find the magnetic field is outside it. So result is same. So here the magnetic field V will be proportional to I, and V is proportional to 1 by R. V is proportional to I, and V is inversely proportional to 1 by R, where small r is 1 by R is the distance of the point P from the center of this cylinder. So this is the one case. Now second case is if the point P is inside the conductor. Now suppose this is the same cylinder whose radius is capital R. Now second case we will consider the point where we want to find the magnetic field is inside the cylinder, means the distance of this point P from the center is small r, and small r is less than capital R. In earlier case, the small r was greater than capital R, means that point was outside. Now here point is inside the cylinder. Construction is same. The length of this cylinder is very large. Total I current is passing through it, and the current I is passing uniformly throughout the area of cross section of this cylinder. Now we want to find the magnetic field at a point P which is inside the conductor and distance is small r from the center. Then here we will construct a empyreal loop whose radius is small r and this will be the small r. So this will be empyreal loop. Now the first we will find what is the current through this cylinder whose radius is small r. That we can find the what will be current density. Current density here will be equal to the current I divided by pi I square. And now what will be the current which is passing through the radius or the area of cross section pi small r square will be equal to I dash will be equal to I bata pi r square. This is the current density for, and we multiply the area of cross section of this cylinder whose radius is small r, pi r square, pi will cancel, and this will be equal to I into r square divided by capital R square. So this current will be definitely less than I because capital R is more than small r. So now the current we will consider inside the cylinder is I dash, not I. Now we will apply the Ampere circulatory law. Now by the Ampere circulatory law, line integral of B inside dot dl will be equal to mu 0 summation of I. Now here also the direction of magnetic field will be inside the board perpendicular and the magnetic field will be same at each point of the empyreal loop. So we can consider that B is constant and we will take outside. Now the angle between DL and B is 0 because B is always tangential to it. So B and DL will be in the same direction. So theta is equal to 0. So the line integral will be here BDL will be equal to BDL cos 0. So here the summation of current is I dash is equal to this much which we have find it. So now using this the line integral of B dot dl will be equal to B dl cos 0 and cos 0 is equal to, so we directly write B into dl is equal to mu 0 times I dash and I dash is equal to I r small r square bata capital R square. Now B is constant, so we take B outside. Then the line integral of dl, the line integral of dl will be same as the circumference of the circle whose radius is small r. So it will be equal to B inside, so we write B in into the dl will be equal to 2 pi r which is the circumference of the empyreal loop will be equal to mu 0 into I small r square bata capital R square. So B in here will be equal to mu 0 bata 2 pi I bata r square into small r. Here one r will cancel. So here mu 0 is constant, I is constant, 2 pi is constant, r square is constant. So the B inside is proportional to r. For the earlier case, when it was required, it was inversely proportional to r. So B inside the magnetic field inside the cylinder will be proportional to I and proportional to small r. So we can also write B inside will be equal to B outside into small r bata r. We have used the value of B outside which is equal to mu 0 bata 2 pi I bata r square. So B inside will be equal to B outside multiplied by small r bata capital R. So the B inside will be equal to 0 as R is equal to 0 means at the center B is equal to 0. Now as R increases here, R increases, then it is proportional, so it will be a straight line, and up to this point, this is the surface point where R is the radius of the cylinder. So here the magnetic field will be maximum. Here it will be equal to V maximum, and V maximum will be at the surface. And if we are going outside it, then the B is proportional to 1 by R. So as distance increases, it is decreasing and it will be hyperbolic one. So here we can have the graphical representation of the magnetic field. Here the magnetic field is 0 at the center, means at the center of the cylinder, and as small r is increasing, then V is increasing up to the radius, then it will be outside. So in outside, V is proportional to 1 by R. So V will be increasing as R. V will be decreasing as R is increasing. So V is here 1 proportional to 1 by R. So therefore, we can write V is equal to V0 I bata 2 pi R into R square into capital R. If we want to find at the surface small r will be equal to capital R. So we put small r is equal to capital R. This R will cancel. So B will equal to V0 I bata 2 pi R, and it is maximum. B is maximum at the surface. On the surface of cylinder, the magnetic field is maximum and its direction is again same, that is perpendicular to the board inside. Now what will be the, how the magnetic lines of force will be there? If this is a conductor is there, we take whether it is a cylindrical conductor or thin conductor, and I current is passing through it, then the magnetic lines of force can be given by the right hand thumb rule. If thumb indicates the direction of current, then the magnetic lines of force are governed by, or they are in the curvature of the finger. So it is then, it will be this side. So it will be anti-clockwise. If we reverse the current, here the current, direction of current is upward, here the direction, we reverse that, then it will be downward. Current is downward. So here it will be a, now the circulation will be opposite to it. Here it was in the counterclockwise direction. Here it will be in the clockwise direction. So if we simply change the direction of current, then the direction of magnetic lines will be in the opposite direction in both the cases. Okay.